In this video, we will cover topics like the atomic number, the average atomic mass, the mass number, and the number of protons and neutrons. You will have a chance to test your understanding with short practice questions. Then we will dive deeper and work through a practice MCAT-style passage. We will review each question in detail, and I will share practical tips to help you analyze passages and choose the best answer more consistently. Let's begin. So on this slide, you see a picture of elemental chlorine right here as it appears on the periodic table, along with an isotope of chlorine, chlorine 37, right here. Different values are shown for each, and we are going to discuss in more detail what those values represent. Specifically, we will explain the atomic number, the average atomic mass, or sometimes called the atomic weight, and the mass number. Let's begin with the atomic number, which is often written as the letter Z. The atomic number is the number of protons in the nucleus of an atom. It serves as a unique identifier of each element, almost like an ID card. On the periodic table, the atomic number is the smaller of the two numbers listed for each element. For chlorine, the atomic number is 17. This means that every chlorine atom, no matter which isotope it is, contains 17 protons. For example, both elemental chlorine on the periodic table and the isotope chlorine 37 have an atomic number of 17. All chlorine atoms, including all of its isotopes, share the same atomic number. Next, we will explain the average atomic mass, which is sometimes called the atomic weight. The average atomic mass is the weighted average of the actual isotopic masses of all the naturally occurring isotopes of an element. The equation for the average atomic mass is equal to the sum of the isotope mass times the relative abundance. It is measured in atomic mass units or AMUs. On the periodic table, this number is typically the larger of the two numbers shown for each element, and it is usually expressed as a decimal value. For example, the average atomic mass of elemental chlorine, as shown on the periodic table, is about 35.5 AMU. Let's now describe the mass number. The mass number is the sum of the protons and neutrons in the nucleus of an atom. The equation for the mass number is equal to the number of protons plus the number of neutrons, or the mass number is equal to the atomic number, which is equal to the number of protons plus the number of neutrons. The mass number is defined for a specific isotope, and it is written in isotope notation as shown here for chlorine 37. The mass number varies between different isotopes of the same element. Unlike the average atomic mass, the mass number is always a whole number. For example, in chlorine 37, the mass number is 37, while the atomic number is 17. On this slide, note the mass for a proton, a neutron, and an electron. Protons and neutrons have roughly the same mass, while an electron weighs about 2,000 times less than the mass of a proton and a neutron. Now, you do not need to memorize these values for the MCAT. They are shown here just to help you get a sense of how the masses of atomic particles compare to each other. Here, we are going to explain isotopes in more detail. The standard definition of an isotope is an atom of the same element that has the same number of protons but a different number of neutrons. Because isotopes have the same number of protons, they belong to the same element and share the same atomic number. However, they differ in their mass number and in the number of neutrons. The chemical reactivity of isotopes is essentially the same because they are composed of the same element and they have the same number of electrons, especially the same arrangement of valence electrons. On the other hand, isotopes often have different physical properties because the number of neutrons in their nuclei is different. Examples of physical properties that can vary include density, nuclear stability, and radioactivity, all of which depend on the number of neutrons and the nuclear structure. Examples of isotopes include chlorine 35 and chlorine 37, which are the two isotopes of the element chlorine. Now, in this slide, we will explain how to calculate the average atomic mass, which is sometimes called the atomic weight. The average atomic mass of each element is always provided on the periodic table. However, the atomic mass of a specific isotope is not shown on the periodic table. Instead, it will be given to you in a question stem or a passage. The formula for the average atomic mass is average atomic mass equals the sum of the isotopic mass multiplied by the relative abundance. The relative or percent abundance is the percentage of atoms of a specific isotope of an element compared to the total number of atoms of all isotopes of that element found in nature. Here are the steps you can use to calculate the average atomic mass. Step number 1 requires that you write down each isotope's mass in AMU, or atomic mass units. The second step requires that you write down each isotope's natural abundance. If the abundance is given as a percentage, convert it to a decimal by dividing your percentage value by number 100 or by moving the decimal 2 places to the left. Then multiply each isotope's mass by its decimal abundance. Finally, in the last step, we need to add the results together. The sum of the values is the average atomic mass. On the next few slides, we are going to provide you with some basic practice problems so you can test your understanding of the concepts you just learned. It is best advised for you to pause the video for each practice problem so you can practice the problems on your own and then come back to the video to see the solutions to the problems. So here's question number 1. It reads, calculate the average atomic mass of the two naturally occurring isotopes of chlorine using the information provided below. Chlorine 35 has an atomic mass of 34.97 AMU. Its percent abundance is equal to 75.8%. Chlorine 37 has an atomic mass of 36.97 AMU, and it also has a percent abundance of 24.2%. Here is the solution to the problem. We will follow the steps outlined on the previous slide. Step 1 is already complete because the question stem provides the atomic masses in AMUs. In step 2, we need to convert the percent abundances to decimal form. We can do this either by dividing the percentages by 100 or by moving the decimal point 2 places to the left. Doing so gives us a value of 0.758 for chlorine 35 and 0.242 for chlorine 37. Next, in step 3, we need to multiply each isotope's mass by its corresponding decimal abundance. So for chlorine 35, we need to multiply 34.97 by 0.758 to get a value of 26.52. For chlorine 37, we need to multiply 36.97 by the value 0.242 to get a value of 8.95. Finally, step 4 requires us to add these values together. So when we add 26.52 and 8.95, we get a final value of 35.47 AMU. Therefore, the average atomic mass of the two naturally occurring isotopes of chlorine is 35.47 AMU, which is consistent with the value shown on the periodic table. If you round 35.47, you will get a value of 35.5 AMU. Here's question number 2. It reads, for each of the following elements, identify its atomic number and average atomic mass. So this question is asking us to figure out the atomic number and the average atomic mass. Now, let's briefly review the two concepts. The atomic number is the number of protons in an atom, and it is usually shown as the smaller whole number on the periodic table. The atomic number uniquely identifies each element and it determines its position on the periodic table. The average atomic mass is the weighted average of the actual isotopic masses of all the naturally occurring isotopes of an element. It is usually shown as the larger number on the periodic table and is expressed as a decimal value. So here, the atomic numbers of the four elements are provided at the top. So the top number is the atomic number, and the lower number or the average atomic mass. The atomic number of gold is 79 and its average atomic mass is 196.97. The atomic number for manganese is 25 and its average atomic mass is 54.94. The atomic number of calcium is 20 and its average atomic mass is equal to 40.08 AMU. The atomic number of selenium is 34 and its average atomic mass equals 78.96 AMU. Question number 3. It says provide the atomic number, average atomic mass, and the mass number for the following elements where applicable. Here we are asked to write the mass number as well as the atomic number and the average atomic mass of the following element. Take a minute and think about this question. Come up with the answer, then come back and check how you did. The first two are two isotopes of lithium. They have the same number of protons, but they differ in the number of neutrons. Lithium atom in option A has an atomic number of 3 and a mass number of 6. Mass number is equal to the sum of the number of protons and neutrons. So if our lithium atom has a 3 for its atomic number, it means that it has 3 protons. So then it should have 3 neutrons to give us a value of 6 for the mass number. The lithium atom in option B is the second isotope of elemental lithium. It has an atomic number of 3 and a mass number of 7. So it would have to have 4 neutrons in its nucleus to give us a value of 7 for the mass number. As you can see, for the options A and B, the mass numbers are listed at the top number, and the atomic number is listed at the bottom. And both of the lithium isotopes, have a number 3 for atomic number. Notice that the values of 6 and 7 are mass numbers, and they are not the average atomic mass. Mass number is the sum of the protons and neutrons and is presented in isotope notation as a whole number, not a decimal. In option C, 3 is equal to the atomic number, which is the number of protons, and 6.94 is the average atomic mass. And on this slide, I have listed the number of protons for the two isotopes of lithium. So in option A, lithium 6 has 3 protons and 3 neutrons. In option B, lithium 7 has 3 protons and 4 neutrons. Now here's a question for you. From options A and B, which one would you say is more abundant? Is lithium 6 more abundant or is lithium 7 more abundant? The average atomic mass of lithium is 6.94 AMU, which is much closer to 7 than 6. Since the average atomic mass is a weighted average, the isotope that contributes most to the average must be the most abundant isotope. So lithium 7 in, in option B is more abundant. Here's question number 4. It reads, which of the following hypothetical atoms is an isotope of silver? And the options A, B, C, and D are listed. What do you think is the answer to this question? So recall that isotopes of the same element have the same atomic number, or Z, the atomic number, but different mass number. So we need to look for an option that has the same atomic number as elemental silver. Elemental silver has an atomic number of 47. All atoms of silver, including its isotopes, have an atomic number of 47. Isotopes of silver have different mass numbers, but their atomic number, which is the number of protons, is always the same. The only option that matches our explanation is answer choice C. So answer choice C is the correct answer. Question number 5. It reads, write the number of protons and neutrons for the following elements. Option A, it has listed oxygen 18. Option B has listed oxygen 16. And option C has listed vanadium. So for option A, we have 18 for the mass number and 8 for the atomic number. The reason why 18 is the mass number and not the average atomic mass is because 18 is represented as a whole number and not a decimal number. So 18 is the mass number. The formula for mass number is the sum of protons and the neutrons. So oxygen 18 has 8 for its atomic number, which is the number of protons. To figure out the number of neutrons, we need to simply subtract 8 from 18 to get a value of 10, which corresponds to the number of neutrons. So oxygen 18 has 8 protons and 10 neutrons. Oxygen 16, however, has a mass number of 16, which is the sum of the number of protons and neutrons. It has 8 protons and 8 neutrons. Oxygen 16 and oxygen 18 are isotopes of the elemental oxygen, which explains why they have different numbers of neutrons. So option C is a little different. The value of 50.94, is that the mass number or the average atomic mass? What does this number represent? What do you think? Is it the mass number or is it the average atomic mass? So since 50.94 is a decimal value, it is not the mass number. 50.94 represents the average atomic mass. This is important to know. One cannot determine the exact number of neutrons from the average atomic mass values. The exact number of neutrons can only be found from a specific isotope's mass number, not from the average atomic mass. So for option C, the exact number of neutrons cannot be known from the value that is provided. They need to give us the mass number for one of the isotopes of vanadium. You can estimate the number of neutrons using the average atomic mass, but this will only be an approximate value. Another way of finding the number of neutrons is to round the average atomic mass to the nearest whole number. However, this will only be an approximate value. So vanadium 23 has 23 protons, and after we round 50.94 to 51, we get a value of 28 for the number of neutrons, because 51 minus 23 is equal to 28. So vanadium has 23 protons and an approximate value of 28 neutrons. Question number 6, it reads, based on the values provided, which isotope of boron is more abundant? We went over a question like this before in the previous slides. Which isotope of boron do you think is more abundant from the information provided? So to answer this question, we need to pay attention to the average atomic mass of boron. We need to obtain that information from the periodic table. The average atomic mass of boron, as presented on the periodic table, is 10.81. This is the weighted average mass of the two naturally occurring isotopes of boron. This number is closer to 11. So boron 11 contributes more to the average atomic mass. So it is the more abundant isotope out of the two options. And option B, is the correct choice. Now that you have worked through some practice problems, let's now work through a practice MCAT passage to see how these concepts we just learned are tested on the actual MCAT exam. As you read, keep your attention on the main idea of the passage. Details are important, but do not get stuck on them. Instead, highlight or note where they appear so you can easily return to them if a question asks about them. I will read the passage and the questions to you, but take a few minutes to work through the passage on your own first. Afterwards, we will go over the passage outline, we will analyze the passage, and we're going to work through the solutions together. So here's the passage. In a study measuring muscle protein synthesis, MPS, scientists use deuterium oxide in place of regular H2O. Deuterium D is another stable form of hydrogen that contains one neutron in its nucleus. Subjects in the study were given 400 ml of D2O to drink the day before the experiment. The D2O becomes incorporated into body water pool, and from there it is incorporated into the non-essential amino acid alanine. On the day of the experiment, each subject was fed 20 grams of essential amino acids, or EAAs, to standardize anabolic conditions across all participants. Muscle samples from each study subject were collected to measure FSR. The fractional synthesis rate, or FSR, of MPS was calculated using the following formula. FSR is equal to delta ALA, which stands for alanine, over divided by the delta P times T. Delta ALA is the amount of isotope labeled alanine incorporated into muscle protein between biopsies. Delta P is the enrichment of D2O in the precursor pool, and T is the time interval between biopsies. The fractional synthesis rate, FSR, is a measure of how quickly new muscle proteins are being synthesized relative to the total amount of protein already present in the muscle. FSR was measured during both the FSR was measured during both the post-absorptive basal state and the postprandial after EAA consumption state, as shown in Figure 1. Figure 1 says FSR measurements after D2O incorporation. Here's Figure 1. Question number 1. Based on the information given, which of the following correctly represents the isotope notation of deuterium? Option A, B, C, and D are provided. Question number 2. What is the primary difference between the element used to trace alanine in the body of the study subjects and atomic hydrogen? Answer choice A says its FSR value is lower than the atomic hydrogen. Answer choice B says it can undergo nuclear reactions faster than atomic hydrogen. Answer choice C says it has a different mass number than atomic hydrogen. And answer choice D says it has a different atomic number than atomic hydrogen. Question number 3. After D2O is incorporated into muscle protein in the form of alanine, how can it be detected and measured? Answer choice A says this radiolabeled tracer emits radiation that is detected by a Geiger counter. Answer choice B. The nucleus of deuterium is unstable and its decay products can be measured directly. Answer choice C says the heavier mass of this stable isotope can be detected using mass spectrometry. Answer choice D says once incorporated, the deuterium undergoes specific reactions with surrounding molecules which can be detected. Question number 4. It says suppose that another element, X, with a superscript of 4 and a subscript of 2, were used in place of D2O to trace alanine incorporation into muscle protein. How would this substitution likely affect the fractional synthesis rate FSR measurements? Answer choice A says the FSR measurements would not change compared to D2O. Answer choice B states the FSR measurements could not be detected. Answer choice C says the FSR measurements would increase. Answer choice D says the FSR measurements would decrease. So after you have worked through the passage by yourself, come back and let's analyze the passage. So here we're going to briefly review the passage and analyze its main components. The first paragraph serves as an introduction, which explains the purpose of the study. The purpose of the study is to measure muscle protein synthesis using D2O. It also describes how deuterium differs from the hydrogen found in regular water. It is important to note that deuterium is an isotope of hydrogen, which contains one additional neutron in its nucleus. Paragraph 2 and 3 discuss the methods used in the study. The key point here is that D2O becomes incorporated into alanine, which is a non essential amino acid. Recognizing this helps you to connect the labeling method using D2O to how the synthesis of new muscle protein can be tracked. Paragraph number 4 explains how to calculate the fractional synthesis rate, FSR, and it provides the formula and it defines what each variable represents. The final paragraph presents the results, showing that FSR was measured at two different time points and it is accompanied by a graph. The graph demonstrates that FSR during postprandial state or after consuming the amino acids is higher than at the post-absorptive state. So overall, the main idea of the passage is that the study used D2O, which is the study used deuterium, which is an isotope of hydrogen, to measure muscle protein synthesis. So here's the solution to question number 1. Question number 1 reads, based on the information given, which of the following correctly represents the isotopic notation of deuterium? This question is asking you to write the isotope notation for deuterium. You are not expected to memorize the isotopic notations for any of the elements. To answer this question, you need to refer to the passage and use your background knowledge. The passage states that deuterium is a stable form of hydrogen that contains one neutron in its nucleus. From your background knowledge, you should know that regular hydrogen contains one proton and zero or no neutrons. Deuterium, however, contains one proton and one neutron in its nucleus. Therefore, the atomic number of deuterium, which equals the number of protons, is 1, and the atomic mass, which equals the sum of the protons and neutrons, is 2. So option D is the correct answer because it shows 2 as the mass number and it shows 1 as the atomic number. Question number 2 reads, what is the primary difference between the element used to trace alanine in the body of the study subjects and atomic hydrogen? This question is essentially asking you to identify the difference between deuterium and atomic hydrogen. Although the question stem does not explicitly mention deuterium, the element used in the study to trace alanine in the subject's bodies is in fact deuterium, which was administered by having participants drink D2O, deuterium oxide, instead of regular water. If we break this question down further, it is asking about the characteristics of isotopes. Let's go through each answer choice to see which one is the correct answer. Answer choice A states that the FSR value of deuterium is lower than that of atomic hydrogen. This is not the correct answer because the passage does not mention any difference in FSR or fractional synthesis rate between D2O and H2O. FSR measures how quickly new muscle proteins are synthesized, not the properties of hydrogen isotopes. Answer choice B claims that deuterium undergoes nuclear reactions faster than atomic hydrogen. This is not correct because the passage clearly states that deuterium is a stable form of hydrogen, meaning it does not readily undergo nuclear reactions. Answer choice C states that deuterium has a different mass number than atomic hydrogen. This option is correct. One of the defining characteristics of an isotope is that it has the same number of protons but a different number of neutrons, which results in a different mass number. Deuterium has one proton and one neutron, while atomic hydrogen has one proton and no neutrons. Answer choice D says that the deuterium has a different atomic number than atomic hydrogen. This is incorrect because the atomic number equals the number of protons, and all isotopes of the same element have the same atomic number. The atomic number defines the element itself. The correct answer is C. Deuterium has a different mass number than atomic hydrogen. Question number 3 reads, after D2O is incorporated into muscle protein in the form of alanine, how can it be detected and measured? This question is asking how researchers were able to detect the presence of D2O inside the newly synthesized muscle protein. When reading this question, some students may panic because the answer is not stated explicitly in the passage and they may not have the background knowledge to know exactly how an isotope is incorporated into protein can be detected. To answer this type of question, you must think critically. Even if you do not know the exact method, you can use clues from the question stem and answer choices to reason your way to the correct answer. So, from the passage, you know that deuterium is an isotope of hydrogen. As an isotope, it contains one proton and one neutron, whereas atomic hydrogen contains only one proton. So, this extra neutron makes deuterium's nucleus slightly heavier than that of hydrogen. Therefore, we should look for an answer choice that identifies this difference in mass between alanine labeled with regular hydrogen and alanine labeled with deuterium. Answer choice A states that this radiolabeled tracer emits radiation that is detected by a Geiger counter. This is not correct because the passage states that deuterium is a stable isotope. It does not have an unstable nucleus, so it will not undergo nuclear decay or emit radiation. Answer choice B states that the nucleus of deuterium is unstable and its decay product can be measured directly. This is not correct for the same reason as A. Deuterium is a stable isotope of hydrogen and does not undergo nuclear reactions in this study. Answer choice C states that the heavier mass of the isotope can be detected by mass spectrometry. This is correct. As we discussed, deuterium contains one extra neutron, making it slightly heavier than hydrogen. Mass spectrometry can detect these small differences in mass, which allows researchers to measure the incorporation of deuterium into alanine and therefore into muscle protein. Answer choice D states that once incorporated, deuterium undergoes specific reactions with surrounding molecules that can be detected. This is not correct because the passage states that deuterium is stable and does not readily undergo additional chemical reactions. So option C, is the correct answer, and the heavier mass of the stable isotope can be detected using mass spectrometry. Question number 4. It says suppose that another element, X with a superscript of 4 and a subscript of 2, were used in place of D2O to trace alanine incorporation into muscle protein. How would this substitution likely affect the fractional synthesis rate FSR measurements? This is a classic think beyond the text question. Sometimes the MCAT presents scenarios that require you to apply both your background knowledge and the information from the passage to new situations that is not explicitly described. This question is asking what would happen to FSR measurements if a new isotope were used instead of D2O. Let's analyze this new isotope. The notation X with a superscript of 4 and a subscript of 2 indicates that this element has a mass number of 4 and an atomic number of 2. This means that it contains 2 protons and 2 neutrons. As we have learned, the atomic number serves as an identification number for an element. It tells us which element it is. All isotopes of a given element share the same atomic number, since the number of protons defines the element itself. In the case of hydrogen and its isotope deuterium, both have the atomic number of 1, which identifies them as hydrogen atoms. However, this new scenario, the element X has an atomic number of 2, which means it is helium, and it's not hydrogen. Now, here's a question for you. Let's think critically. Can we use helium to trace the incorporation of alanine into muscle protein? Can helium be incorporated into alanine molecules? What do you think? The answer is no. The amino acid alanine is composed of carbon, hydrogen, oxygen, and nitrogen. It does not contain helium. Because helium is a noble gas and does not form chemical bonds with other atoms under normal conditions, it cannot be incorporated into alanine or any other organic molecules. Therefore, if helium were used in place of deuterium, it could not be incorporated into muscle protein, and FSR, or fractional synthesis rate, could not be measured. So, in conclusion, the substitution of this new isotope for deuterium in D2O would not allow the incorporation of the tracer into alanine and thus makes FSR measurements impossible. So, answer choice B is the correct answer. So, in summary, we reviewed the concepts of atomic number, average atomic mass, and how to calculate it. We also discussed isotopes and mass number. In addition, we completed several practice problems and worked through a full MCAT passage along with its solutions. I hope you found the information in this video helpful. If you enjoyed the content of this video, please like and subscribe. I will be releasing more videos like this, so don't forget to hit the notification bell to stay updated whenever a new video is posted. Thank you for watching, keep learning, and happy studying.